All right, in 16.9, we're going to look at acid-base properties of salt solutions, and we're going to actually look at 4 different kinds of salt solutions. Remember, salts are any kind of ionic compound, being a positive and a negative, a non-metal and a metal. So we're going to see things like KF or NaCl or NH4Cl, things like that. Okay, so we're going to start off with the very easy ones here, which are salts that produce neutral solutions. Because if we have these ionic compounds dissolved in water, what's going to happen is the positive and the negative are going to split, and so we end up with like the positive metal and the negative non-metal in the solution. And when it interacts with water, sometimes it'll make the solution a little more basic, sometimes it'll make it a little more acidic, and sometimes it'll just be neutral. And so we're going to look at which kinds of salts produce these different solutions. And the neutral ones are the easiest ones. So salts are those ionic compounds. Okay, we're going to have something, for example, like NaCl, like I gave a minute ago. We're going to have Na plus and Cl minus when you have it in water. Remember, we're also going to have water, which means we're going to have some H2Os, some H pluses, and some OH minuses. So what we're going to look at is what each parts of water this Na is going to react with and which part of water that Cl minus is going to react with. Well, the chlorine is a negative, so it's going to want to try and find something in water where it can take a proton. So if it reacts with water here, we're going to end up with HCl. It's going to take one of the H pluses, and then we're going to end up with some more OH minus. If the Na plus were to react with water, which it could because it's in the same solution or in the same beaker as that, if I react that with water, it's going to not go with the H plus because it is positive itself. It's going to go with the OH part. So I would make NaOH and then H plus. Now the problem with these reactions is that they're not actually going to happen. And the reason they're not actually going to happen is because of what they form. When the chlorine reacts with water, it's going to form HCl. HCl is a strong acid. Strong acids like to be dissociated or apart. They're not going to recombine. Okay. Na plus, when it reacts with water, is going to make sodium hydroxide. Well, sodium hydroxide is a strong base. And strong bases are strong because they are essentially all dissociated into Na plus and OH minus. So it's not going to want to make NaOH. The ions are going to stay in solution. So your ions stay in solution because the conjugate bases and conjugate acids are not strong enough and don't want to recombine or don't want to take something from water. Water is stronger than they are. The acid or the base is stronger. So the reactions won't happen to make anything acidic or basic because if this top reaction would happen, it would make it a little basic. If this reaction would happen, it'd make it a little bit acidic. So this is what we're actually going to get. If you take NaCl and put it in water, you're going to make a neutral solution. So if you have something from a strong acid or something from a strong base, so if I have the conjugate base of a strong acid, which would be the Cl minus, or if I have a conjugate acid of the strong base, which would be the Na plus, these reactions that are going to produce a neutral solution, because neither one is going to make it basic or acidic. Well, if we look at the next example, which does make our solution basic, it means one of them is going to affect and actually is going to interact with water and to make something different. Whereas with the Na and the Cl, I might be interacting with water, but it's not actually producing anything in a reaction. It's not actually interacting with it and forming something. They're just both there. Okay. So if I have, for example, something like NaC2H3O2, so we're going to see what each of these would do with water. Well, again, I'm going to have my little beaker. This is going to be ionic. It's going to break apart. So I'm going to have Na plus and then my C2H3O2 minus. Since I'm in water in a solution, I want to have my H2O. I'm going to have some H plus and I'm going to have some OH minus. So the thing to look at is what is going to react with what. Okay. Well, the Na we just looked at. Okay. If Na were to react with water, we would have Na plus and it would react with water. And like I just wrote down a minute ago, okay, I would have Na OH and H plus. Well, this reaction's not going to happen. I'm forming a strong base, okay, which means that if anything's going to affect my pH of my solution, it's going to be the C2H3O2. So C2H3O2 minus, if it reacts with water, is going to form, well, this is a base, it needs another H, it has a minus, so it's going to need a positive to go with it. So I make HC2H3O2. Left over of water is the OH minus. Okay. Well, this is not a strong acid, that is a weak acid. And weak acids are happy staying together a little bit. Actually, most of them still stay together, and they very rarely break apart very much and go the other direction. So this reaction is going to go a little bit back and forth. If this reaction goes a little bit back and forth, we are forming OH minus. OH minus is a strong base ion, so we're going to become more basic. Okay, so the C2H3O2 is the thing determining my pH for my solution. And it's basic because you have the extra OH minus. Now, you're going to use a Kb value when we talk about these later because this C2H3O2 is a base. It is the conjugate base of a weak acid. So when I look at it from this direction, I'm talking about using a Kb value. So you've got to be very careful because this is acting as a base. Even though it's the other half and forms an acid, Kas are in terms of the acid on the left and the products on the right of it falling apart. This is flip-flopped. Okay? So if my cation, or the positive, okay, is neutral, and my anion is the conjugate base of a weak acid, we're going to get a basic solution. So you got to look at what is interacting with water, what's going to actually form in the reaction, and then what we're going to actually have left over, extra H plus or extra OH minus. In this case, we're extra OH minus. So let's go ahead and look at an example. All right, what is calculate the pH of a 0.30 molar solution of NaF. The Ka value of HF is 7.2 times 10 to the negative fourth. Like I had mentioned in an earlier video, it's way more common to get the Ka values than to get Kb values. You can figure out one from the other, which is why they tend to go with one route, just using Kb's for, or Kas for pretty much everything. So I have NaF. So I have a salt here. I don't have HF. I don't have NaOH. I don't have any other kind of strong acid or strong base. I have a salt. So Na plus, like I mentioned many times here, okay, this is going to break apart in my solution into Na plus and F minus. So I got to see what's going to react with water. And Na plus with water is going to make what I've been saying here all the time is NaOH and H plus, but that does not happen. This is a strong base, so that reaction is not going to do anything. It's not going to actually dictate my pH. So instead, I look at the F minus, which would make sense because they're giving me a Ka value here for HF. Notice how there's F's there. They're giving you some information you need. Well, F minus with water, okay, is going to make HF and OH minus. Well, HF is a weak acid, so we're good because weak acids, like I said before, are going to stay together, or a very small amount actually dissociates. So we are going to form HF. It is going to stick together and stay together, which means we're going to have extra OH minus, which means my pH better be greater than 7. Okay? So how much greater? Well, this is our ice table is coming into play here. Well, if I have 0.3 molar solution of NaF, that means I have 0.3 molar of the Na and 0.3 molar of the F, 1 to 1. So if I've got 0.3 molar of the F, I don't care about the water because water is a liquid. It's going to obviously shift to the right because I don't have anything of these to start with. It doesn't tell me anything about how I have them. So we're going to have X and X. It's going to be 0 plus X if you want 0 plus X, but I kind of skip steps there. This is going to be minus. My Ka value is relatively small, so in all reality, when we do our K here, we're not even going to put the minus X in because it's so small. Well, this is a base, not an acid. It's gaining an H. So I have to use a Kb value. My Kb value is going to be X squared over 0.3. Again, I got rid of the minus X. Well, my Kb value I don't have. They gave me a Ka value. Well, okay, Kw equals Ka times Kb. Kw is the 1 times 10 to the negative 14th. I know my Ka, 7.2 times 10 to the negative 4th. Divide and get my Kb. My Kb value then is 1.4 times 10 to the negative 11th. So that's what I put in over here. And I'm going to get an X value of 2.04 times 10 to the negative 6. Well, that's all great, but that's not my answer. Okay, x here, we're going to know how much it is shifting by. Well, when it shifts to the right, we are not forming H plus, we are forming OH minus. So this right here is my OH minus concentration. Well, it wants a pH. So you can do this a couple of ways. The way I would go is I would take the negative log of this number and get my pOH. I get my pOH to be 5.69. Well, then pH is just 14 minus that. And we're going to get a pH of 8.31, which makes total sense because it is greater than 7. This number here wouldn't make any sense. I'm forming OH minus a base. Okay, acidic solutions now are pretty much not the opposite, but the other thing is interacting now. Okay, when we have acidic solutions, I'll have something like, for example, NH4Cl. Okay, well, when this breaks apart in water, I'm going to have NH4 plus and Cl minus. And so they're going to interact with the water a little bit. My chlorine will interact with the water. This is a negative. It's going to want to join with the positive. So it's acting as a base here. That is a strong acid. Not going to happen, which means my NH4 better happen. So if I have NH4 plus, that interacts with water. What's going to happen here is you are going to form NH3. This NH4 plus is acting as an acid because it is losing a proton. So it loses my H, and I'm left over with NH3. And then you can think of it as H3O plus if you want, because the water is going to gain it, or you can just write it as H plus. Either way, it doesn't make a difference. Okay. Sometimes it's easier for this one to write as H3O plus to see actually where it's going, but it will be H plus, which is the same. So for these, if you have the anion from a strong acid, okay, which means this is the conjugate base of a strong acid, and if I have that, which is from a weak base, so here we're looking at the conjugate acid of a weak base, you're going to end up with something that is acidic, because you are forming here H plus or H3O plus, which is what determines something to be an acid or acidic. Let's try an example. Okay, I've got NH4Cl, same thing, so I just did this a second ago, so I know that my NH4 plus is the stuff that's doing interacting with water to change my pH value. I've got water there. Okay, it's going to lose its H to make NH3 plus H3O plus or H plus, either way. Okay, I start out with 0.1 for the NH4 plus because this is going to split. And so I'm going to have 0.1 of this, 0.1 of that. Well, I don't care about the chlorine. Water, it doesn't do anything, it's a liquid. I don't have any of these to start with. So I'm going to have 0 and 0. So I'm going to put X and X. It's going to shift to the right, obviously. Now here this is acting as an acid, but NH3 is a more common weak base. So actually they did the opposite again and gave you a Kb. So I need a Ka because I need to have X squared over 0.1. Again, remember I'm getting rid of this because it's a small Ka or small Kb. I need to figure out my Ka because it's acting as an acid. So my Kw is Ka times Kb. So I have 1 times 10 to the negative 14th equals my Ka I'm looking for times 1.8 times 10 to the negative 5th. And my Ka for NH4 plus is going to be 5.6 times 10 to the negative 10th. So I'm going to go ahead and I'm going to plug that in. I'm going to get my X value, multiply and take the square root, and I'm going to get an X to be 7.5 times 10 to the negative 6th. In this case, it is my H plus concentration because that is my X. Okay, so now I can just straight up do my pH value, which is going to be pH is going to be negative log of my X. So my pH value is 5.1, which makes sense because it is less than 7. It's producing an acidic solution because I have an H plus there. Now there is one last type of salt solution. It's where both ions contribute to your pH level. The last two we've looked at, only one of them does. These get a little bit trickier. We're not going to do any math with these, but you should be able to kind of figure it out just in general as to whether it's going to be acidic or basic or neutral. Well, if my Ka is greater than my Kb, and that means my pH is going to be less than 7 because the acid is the stronger one. Okay, if I have a Kb be greater than my Ka. My pH should be greater than 7 because the base is stronger. And then the last one, this one's easy. If the Ka is equal to my Kb, then obviously my pH is going to be 7 and it will be neutral.